Welcome. In this video, we will look at how to write numbers in engineering notation. In prior videos, we've talked about how computers store numbers and that they use a base 2, a binary system with only 2 digits, them being 0 or 1. But we haven't really talked about how then the computer stores these binary numbers. And it turns out that the numbers are stored as binary floating point numbers in engineering notation. So what is that? A floating point number in engineering notation. So let's start out with decimal numbers because we're all familiar with decimal numbers. A decimal number in engineering notation has the following form. It has exactly one non-zero digit to the left of the decimal point. And then we call this a decimal digit dot. Decimal digits following. We call this part the mantissa. And the p that is in the 10 to the power p, we call this the exponent. Now, how do we convert a regular floating point number to engineering notation? Well, at its heart, it's a pretty simple algorithm. All we need to do is we move the decimal point either to the left or the right until there is a single non-zero digit that is left to the left of the point. And moving the point one place to the left would increase the exponent p by 1, and moving the decimal point one place to the right will lower the exponent by 1. So let's do an example here, the number 47.11. If I write this number, I really have 47.11 times 10 to the power 0, right? Because 10 to the power 0 is just 1, so 47.11. Now, in order to turn this into engineering notation, right now I have 2 digits to the left of the point. So therefore, I have to move this point, the decimal point, over by 1 spot to the left. So that would be equal to 4.711. And if I move the decimal point over 1 spot to the left, then I have to increase the exponent by 1. So I have to increase it from 0 to 1. And now I have just a single digit to the left of the decimal point. And that is non-zero, right? It's a 4. So therefore, this number would now be in engineering notation. OK, let's do the next number as an example. 0.04711. Well, there is not a single non-zero digit to the left of the number. So therefore, this number is not in engineering notation. But let me write this with in the following way. 0.04711 times 1. So times 10 to the power 0 to see what the exponent is, that it is currently just 0. And now in order to turn this into an engineering notation number, I have to move the digit over, I have to move the decimal point over to the right. How many spots? Well, I have to move it here, right? If I move it there, I would have 0.4711 times 10 to the power 1. Times 10 to the power negative 1. Why? Because I have to lower the exponent if I move my decimal point over to the right. But this is still not in engineering notation, right? Because I have a 0 to the left of the point. So I have to move this point over 1 more spot. So that would be equal then 4.711 times 10 to the power. I move the decimal over to the right, so I have to lower the exponent by 1. So negative 1 minus 1 is 10 to the power negative 2. And now this number, 4.711 times 10 to the power negative 2, is in engineering notation. OK. Now, we can do the exact same thing in binary. Right? Nothing really changes. The naming is a little bit different, and there's one unique feature of binary numbers in engineering notation. Right? We still have the mantissa, but our numbers always start with a 1 to the left of the binary point. The following digits, the b's indicated here, are called, well, they form the mantissa, and we call these digits bits. And when we still have an exponent, except that is taking the power of our base 2 instead of our base 10 in decimal. Now, there always has to be the number 1 to the left of the point, because engineering notation requires that there is a non-zero digit to the left of the point. And the only non-zero digit in binary is the 1. So there has to be always a 1 to the left of the point for an engineering notation number. Now, the exponent p, right, is a number that we can convert to binary if we so wish. But for now, we will just leave it as a decimal number, knowing that we can convert, of course, this decimal number, which is the exponent p, to a binary number as well. Okay, so in order to convert a binary floating point number into a binary floating point number in engineering notation, we again only have to move the binary point to the left or the right until there is a single 1 to the left of the point. So in the example down here, we have 101.11, which is not in engineering notation. And let me just write this 101.11 times 2 to the power 0 to see that the exponent p right now is a 0. And in order to turn this into engineering notation, I have to move the point over to the left. Let's move it by 1 spot. So that would be 10.111. And if I move it over 1 spot to the left, I have to increase the exponent by 1 from 0 to 1. But this is still not an engineering notation, so I have to move this dot over 1 more spot. So this would be equal to 1.0111. I moved it over 1 spot to the left, so I have to increase the exponent by 1 from 1 to 2. Now 1.0111 times 2 to the power 2 is in engineering notation because I have just a single 1 to the left of the binary point. One more example, the number 0.01101. So let me just write this again, 0.01101 times 2 to the power 0 to show that the exponent is 0 in this case. But this is not in engineering notation, and I have to move the point over to the right. I'm going to move it by 1 spot, so that would be equal to 0.1101 times 2 to the power negative 1. Right, I moved the binary point over to the right, so I have to reduce the exponent from 0 by 1 to negative 1. But this still isn't in engineering notation, so I have to move this dot over 1 more spot, which would be equal to 1.101 times 2 to the power, reduce the exponent by 1, 2 to the power negative 2. And that translates the number now into an engineering notation, right? Because I have a single 1 to the left of the binary points. All right, so now let's go back to the algorithm that we developed before that translated decimal numbers to binary numbers. And here's just the summary of that algorithm. Right, it had all these individual steps. And among them was this first step where we calculated the largest power of 2 that was smaller or equal to the number to translate. And that was our p, right? So if we look at this sum over here at the bottom that we had written out, right, you'll see that this one here is the largest power of 2, smaller or equal to the number, which is exactly equal to, right, this one that we have in to the left of the binary point for a binary floating point number in engineering notation. And in fact, this one here that multiplies the 2 to the power p is exactly expressed here as this first term in the number. So if I write this now out, I have the first digit, which is a 1, that multiplies the 2 to the power 4. Then all following digits multiply smaller powers of p from 4 to 3 and so on. You would see that When I do this algorithm, I have basically already translated my decimal number directly into a binary number in engineering notation. I just have to start out with the first number, the first digit here, put the point right there and write the following bits just after the binary point, and then multiply it by 2 to the power p. So this algorithm gives us directly the binary number in engineering notation. Thank you for watching.